Good morning, everyone. Happy Monday. Hope everyone is doing well. Uh, Please email me if you have any questions or anything. Uh, I think some people are falling behind a little bit in the course, so just email me and we can get you caught up. The cat is being obnoxious as usual. So today we're going to start chapter 14. And so this chapter is compounds that contain oxygen, halogens, or sulfurs. And so we'll look at a couple of those groups. So we'll start looking at what are called alcohols. So alcohols are anything. Get out. With an OH group. Sorry, my cat bit me, so I'm not looking at him. We have alcohols. Then we'll also be looking at ethers. And so this is, let's just name it. And so we'll look how to name things. And so part of naming things is being able to identify what groups we have. And so here, this is a tert-butyl group. And this is a methyl. And so this solvent is commonly known as MTBE, or we could see that that stands for methyl, since we're putting things in order alphabetically. So methyl, tert-butyl, and then ether. And so ether just means we have carbons kind of on either side of this. So this RO, R scenario, and they can be different R groups. And so we could just name them by naming the two different groups on there. Then we'll look at different alkyl halides and their names. And then also look at thiols. So thiols or anything with this SH group here. So let's start off with alcohols and just kind of the different types of alcohols there are. So we can have what's called primary, secondary, tertiary alcohol. So this is similar to carbons, how we had primary, secondary, tertiary carbons. And so if we have a primary alcohol, it's going to be connected to a carbon that's connected to one R group. A secondary alcohol, now we only have one hydrogen on the carbon that it's attached to. So it's attached to two R groups. And then a tertiary alcohol is an alcohol attached to a carbon with no hydrogen. So all three of them are R groups there. So then looking at these examples, and so let's practice naming them. So this is my longest carbon chain of 2. And this is a primary alcohol since it's attached to only one other carbon here. And of course, this is ethanol. And then notice we just changed the ending to all for alcohols. So looking at isopropanol, and anybody know what isopropanol is used for in chat? So isopropanol is usually that's called your rubbing alcohol. So usually it's sold in like 70% solution, but you could get it higher if you go to different stores. They say sell isopropanol like pure, and that's really nice for cleaning. And so this is the isopropyl group here. So a carbon attached to two other carbons like this. So this is isopropyl. And so if we add an OH here, that gives us our isopropyl alcohol or isopropanol. And then so looking at this one, so again, we have our tert-butyl group there. There's our tert-butyl, and then OH there, so that gives us tert-butanol. So let's skip over this reaction for now. I just want to talk about other properties. And so alcohols are considered, very polar. And give me 1 second here. Let's just draw it out. Let's get our molecule kits out. So I'm just trying to make ethanol right now. Where are my single bonds? Seem to be. There we go. Couldn't find a hydrogen there for a second. So I have my 2 carbons there for ethane. So I want to make ethanol. And let me just fill in these hydrogens. So another thing you can use if you don't have molecule kits at home are like those spice drops. I don't know if you all know what I'm talking about. They sell them in the bulk section. All right, so there's our molecule. And so what I want to show is a geometry off to you. So notice, so at our oxygen there, of course, we're going to have this bent geometry. And so alcohols, let's do a bit of recap as well. So we said they have that OH group. So this will probably be close to around, 104 or so for our bond angle. And then, so what type of bonding do alcohols have? What type of intermolecular forces, I guess I should have said. And so our hint here is that alcohols exhibit hydrogen bonding. So if you remember, hydrogen bonding is anytime you have hydrogen bonded to nitrogen, oxygen, or fluorine. So of course, if you have an alcohol, this equals H, or hydrogen bonding. And so if you recall from last quarter, hydrogen bonding is very strong. And so I'll just add this. So H bonding, strong intermolecular force. And so that helps hold the molecule kind of together within itself, so that gives it a relatively high boiling point. We can also say that this OH, of course, that also means that it's going to be polar, so any of these alcohols tend to be polar. And then we get this saying like dissolves like. And that just means that substances have to have similar types of bonding. So hydrogen bonding, something that's polar, will dissolve something else that's polar. And so in this case, many alcohols are soluble in water. So I would take, drinking ethanol. That's going to be your primary example, since it's a mixture of ethanol and water. And so let's look at some boiling points. And so now what we're looking at is just a chart of boiling points. And so boiling points are dependent on a couple of things. So of course the size of the alcohol or whatever substance we're looking at. So larger the size, more intermolecular forces, so that gives it a higher boiling point. But then we're also looking at the effects of these hydrogen bonding. So those are going to keep it together. So let me find. So this chain over here is alkanoic acid. Those are acids. And then alkanols. So it sounds like ethanol, methanol at the primary position. So all these have increasing boiling points. Where are ethers? I don't think there are ethers in this graph, unfortunately. But let's just... So alcohols will have relatively high boiling points. Again, that's due to their polarity and hydrogen bonding. But let's look at ether boiling points. So ethers, we said, are anything that kind of looks like this. So let's compare diethyl ether versus ethanol. And so as we make our assessment, we have to kind of compare a couple of things. So we're looking at, again, polarity, and then is there any hydrogen bonding? And so ethers are polar. So they have our electronegative oxygen. So if we were to map this, the electron density would be centered around oxygen here. So kind of, on this side of the molecule. And then the rest would be trying to shade to show. So this would be more positive. That's where our electronegative region is. So here, this is where the electron density is, centered around the oxygen. And so this one has more of what we would say a dipole moment. So a dipole moment, you're just trying to determine how susceptible it is to polarity. And so you can measure the dipole moment. You can look these up as well and kind of guesstimate it. And so let's name these two. So again, two ether groups. So that's going to be diethyl ether. So anytime you see someone talk about ether in lab, it's usually diethyl ether. That's the commonly used ether. And then so this is, we said ethanol. And so this one has, again, our hydrogen bonding and dipole-dipole. So I'm just adding in all those inner molecular forces. And of course, van der Waals or London dispersion. So everything has that. And so in comparison, ether does have some dipole-dipole since it is polar. And it'll also have van der Waals. It would not have hydrogen bonding. And then let's just compare, because the molecular weight is also relevant. And so now I'm going to consult the internet for the following. Since it's just faster. So diethyl ether has a molecular weight of 74 grams per mole. And let's look at ethanol. So ethanol is smaller, only 46 grams per mole. So just based off of van der Waals forces, diethyl ether should have a higher boiling point. But of course, what's actually making the effect is this hydrogen bonding. And so let's compare the boiling point. So the boiling point of ethanol, I believe, is 78. Yes, 78 degrees Celsius. And so for diethyl ether, looking at the boiling point is 34.6 degrees Celsius. And so that's, fairly significant. And again, that's mainly due to that hydrogen bonding for a molecule. So let's practice naming alcohols. So I drew up some examples. I have some examples here. But what we're going to find is our naming So our naming rules are very similar to everything we've been following before. So if you've been keeping up, there should be kind of no surprise. So the first thing is we need to find the longest chain. That has our alcohol. Sorry, trying to keep all plastic away from my cat. And so we'll find the longest chain, and then we'll identify the alcohols. So if multiple, we'll use our prefixes like before. And then the ending changes to all. So let's look at a couple of these examples. So this is 2-methyl butanol, or 2-butanol, kind of depending on the naming convention. So the first thing we need to do, we're looking at this molecule, identify our longest chain. We could do, looks like 1, 2, 3, 4. I better label this. And again, we want OH to have the highest priority now. And so looking at this one, we have an OH on our second carbon here. We also have a methyl on our second carbon. So that's where we get our 2-methyl butane, and then there's 2 for our OH all. And you could also see it, so 2-methyl, 2-butanol as well. Now looking at this next example, we'll do the same thing, identify our longest chain. So it looks like we should start over here. So 1, 2, 3, 4, 5. Now it doesn't matter. 6. And so 1 is on our OH. Now we have 3 and 5 for our methyls. So we can say 3, 5, and then there's 2 of them. So dimethyl. And then you could also say 1-hexanol. Let's do the same for this one. So we could do 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5. Okay, that doesn't seem to work. So let's number it this way. So 1, 2, 3, 4, 5, 6, 7. And so that's how we got the heptane part. And then it has a methyl group here on the 6 carbon. So that's how we got 6-methyl. And then we could also call it 3-heptanol. So this one's a little tricky, in my opinion. So now we're looking at a ring, and we're trying to assign priorities. And so what's kind of odd here is we need to give OH the 1 priority. And so this is 1. We either could go 2, 3, 4, or excuse me, 2, 3, 4, 5. But bromine has a higher priority than chlorine since it's larger. So I actually want to make this 2-bromo. And well, now we have to go in order. So 1, 2, 3, 4, 5. That forces chlorine as 5 there. And so now we can start naming this. So we have cyclopentanol, since again our ring. And so now we just need the first bits on there. So we can have 2-bromo, 5-chlorocyclopentanol. Any questions about naming? Just seeing if there's anything else I want to cover. On the naming there. Okay, I think that's good. So let's start looking at some of these reactions now of alcohols. And we'll do some practice probably on Wednesday. So bring your questions for Wednesday too. And so dehydration of alcohols to form alkenes. And let's look at the mechanism, because it's always important to understand our mechanism. So we're starting with our alcohol. And so if we react it in the presence of an acid, so let's do this H. Let's do sulfuric acid. And I'm writing it this way for a reason. And so we have this OH group here. And so the first step is in the presence of the acid, this OH from our alcohol will get protonated. So now I'm just drawing my protonated species here. And so now this water can act as a leaving group. And so now what's going to happen is we can have another water come along, attack this hydrogen. And so if it's attacking this hydrogen, these electrons have to go somewhere. And so they can go and form a double bond here. And since now we're forming a double bond, now we have this carbon. It would have one too many bonds. And so this means that water will leave. And so water leaves. And that gives us double bond here. And of course, water. So now I want to look at this next scenario and look at it a little bit deeper, this mechanism. And so first of all, let me get my molecule kit out. And give me 1 second to make this. So it's not completely necessary, but it is really nice to have this molecule kit. And so I'm just trying to make this molecule real fast. And the whole advantage and why I'm making a molecule of this is so we can see the 3D shape and what's going on in 3D, because that's what really gives us insight. Maybe I should have used my little OChem kit. Running low on these hydrogens. And if you don't have molecule kits, you can also just try to look at the 3D structures, online, visualize them. Just any tools that are helpful for you. And if you're following along and you have the opportunity to make this, go for it. All right, so now we're looking at our molecule. And so let's look at a couple of things on here. So our alcohol, it's attached to a secondary alcohol. Right, so you can see that. There we go, trying to get that a little bit nicer for you. So there's our OH attached to a secondary alcohol since it only has one H there. And so that's the hydrogen. And then so now let's look at our mechanism. So again, the first step is that this gets protonated. So now that's ready to leave. But then if we're looking at this mechanism, so this is protonated. This is tedious going through the mechanism like this, but at the same time, understanding this mechanism is really important. And that's what kills OChem students. All right. And if you can do this, you're way ahead of the game. So here's our protonated alcohol group now. And so we're looking at it. And so the only thing is, so we're going to attack a hydrogen and it can leave, except if we're looking at this, and this is what's shown in this step right here, or kind of these next two steps. So I'll just highlight where we are for a second. So we're looking at these two steps in detail. Let me slide that down. There we go. And so we're asking ourselves, so which one of these hydrogens so which one of these hydrogens is more favorable to be lost? So are we going to lose this hydrogen and form our double bond here? Or will we lose this hydrogen and form a double bond here? And so that's what we're asking ourselves. So let's go back. Let's go back because I just really want to break this down so we can think of what our products would be. And let me just rewrite this. So again, we're here right now. This is positively charged. Don't forget your formal charges. And CCH3. Don't forget my H's there. HH. So these, again, are two possible protons for attack. So we could deprotonate this one and form a double bond here. Or we could deprotonate this one and form a double bond here. And so what we find that the major product is going to be the more substituted alkane here. So if you compare, so it wants to do it to this carbon since it's attached. We have a primary carbon versus a secondary carbon. So this is more favorable. So this would be the less favorable product. So again, that would look like water coming, deprotonating it here. This would cause a double bond to form. This leaves, so this would be one product. And so you can use your kit to visualize that. Ah. Didn't give myself enough space. And so always count your carbons. So 1, 2, 3, 4. 1, 2, 3, 4. So again, this is our minor product. This would be up here. And then, so let's go back. Let's look at kind of our major product. So what are our options for our major product? So how would that form? Let's look at that. And so we see that losing this hydrogen is probably going to be more favorable. Again, because this is a more substituted carbon, so it has more things on it. And then we have to decide, so if you're losing this, is it going to form trans or cis? So you could have had kind of this rotation like this. But you can kind of see that the trans is more favorable anyways. Because that looks to me where they're in line to be deprotonated. So this will be deprotonated, and then that can leave. But then that'll give you kind of a trans alkene there. And if you find, so this was the major product. This is also more favorable sterically. So usually the trans is a major product unless there's some sort of, mechanism that would make it not the case. And so our cis, where they're on the same side, so this could still happen. These are oriented close. But of course you have some steric hindrance from here, so hence why that's a minor product. And this trans is going to be our major product. Any questions on that part right here? So let's look at other reactions now. So now these are going to be oxidation reactions. And so we have this series of reactions. And so first of all, we want to identify, do we have a primary, secondary, or tertiary alcohol? And so if we have a primary alcohol, again with two OHs, and then if we oxidize it, so anytime you see this little ox, this means oxidation. And so some examples. Let's look at some examples here. And let's look at our mechanism. So let's look at this example. So CH2OH. So this is benzyl alcohol. And so the oxidizing conditions that we're going to use are this chromium oxide, so chromium 6 oxide in the presence of sulfuric acid. And so let's look at this mechanism. So you don't have to know the mechanism, but let's just appreciate it. So we'll start. And this one should be interesting. So we start with our alcohol. And then going to be there in the presence of our chromium oxide. So we have this OH group, electrons on that oxygen. So now it's going to attack this chromate. So we'll make this chromate species. So we still have our H on there. Now I'm just drawing my new bond to chromium. Negative charge on this. And so now we have this negative charge on this chromium oxide. We have a plus charge on our oxygen. And so this means that this is going to attack this over here. And deprotonate it. Let's draw that out. So this hydrogen's gone, still bonded to our chromium. So now that OH is over there. Right, so I just move this hydrogen from over here to over here. And don't forget, two hydrogens over here, so we can kind of do a similar deprotonation mechanism. So we'll have water come along. So it's going to pluck this off. Now these electrons have to go somewhere. So these electrons are going to form a double bond. And then so once they form that double bond, this will leave. And so let's write our product. So now our product let's see, looking for other reactions here. So this would have made here, and then this can go on And so our final product would be an alcohol group over here. So you can see that with this primary alcohol, we can form the aldehyde, or it can continue on all the way to the carboxylic acid there. And so in the case of the secondary alcohol, our option is to form our ketone. So we have our one hydrogen there. But then if we have a tertiary alcohol trying to undergo oxidation, notice that we would have no reaction. So there's no hydrogen for it to pluck off. So just a few other conditions or what you might see. So there's a lot of oxidizing agents. See if you have OH. So we have our cyclohexanol. And then there's this reagent that is called DMP. And so this is another oxidant. You might also see PCC. It's another oxidant. And so this is in the presence of an organic halide solvent. And so this would take this alcohol to the ketone. And whereas in this case, so this kind of did two oxidations and took this all the way to the carboxylic acid. But if you use DMP in the same reaction, so this is our benzyl alcohol again with DMP in the presence of DCM. Now this one gives you benzaldehyde. So it would stop. So let's do some more in your textbook, just so we're all kind of clear on this. Since there are different conditions and everything. So we could have, let's just look at this simple 1-butanol. This is from your textbook. 1, 2, 3, 4. So butanol. And this is just general oxidative conditions. And so our first step converts this to the aldehyde. So 1, 2, 3, 4, 5. 1, 2, 3, 4. So this is our aldehyde. So we started with 1-butanol. We can form butanol aldehyde. And then if we do another oxidation, or if our conditions are harsh enough, then this will go to the acid. So 1, 2, 3, 4. And so this gives us butanoic acid. So let's kind of round out the chapter with ethers and thiols. And so ethers, again, we went over some of the naming, at least for our simple ethers. So this is dimethyl ether. You could also have what's called epoxides, but I wouldn't put epoxides and ethers in the same category. So an epoxide is where you have this ring here. And so ethers, again, are kind of less polar than alcohols. So if all things, everything else is the same, like molecular weight, aka their van der Waals forces, the alcohol will have the higher boiling point. There's also some kind of special ethers. So this is called anisole. And so you could try to name. So what's anisole's IUPAC name? So what would that be? So we have a methyl group and a phenyl group. So another name for this could be methyl phenyl ether. So we also have these oxyrenes. So this can be ethylene oxide or dimethyl oxide, or excuse me, dimethylene oxide, to show that these are bonded. So different names for this. Furans, this is also comes up. So tetrahydrofuran is a very commonly used solvent. So this is THF, and it's going to be extremely polar, very good, very solubilizing. And here's another one. So you have 1,4-epoxybutane. So telling you what positions this epoxy is, and butane. So 1, 2, 3, 4. And then another common group is this dioxane. So this is another great solvent. And so this is 1,4-dioxycyclohexane, or just dioxane. Oh, where did our alkyl halides go? So these alkyl halides are just anything kind of with a halogen. So some common ones. So this is chloroform. Welcome, welcome in the chat. Happily take chemistry questions. So this is chloroform. So it has one chlorine group on there. And so the other thing is many of these are going to be polar. So if you draw it out, so this is polar. So this side's going to be more electronegative. This is more electropositive on this side. So another common solvent, and I think we mentioned it in looking at some of our conditions. So this is DCM or dichloromethane. And this is a great organic solvent, although it is carcinogenic. And so this is also polar. So this side is going to be more electronegative. And this side's going to be more positive. And so size also contributes to the boiling point. And so just comparing boiling points. So let's just compare 1 chloropropane versus 1 bromopropane, like your textbook. So 1 chloropropane versus 1 bromopropane. And so the only difference is the bromo versus the chloro. So propane, 1, 2, 3, Cl, 1, 2, 3, Br. And so you have this difference in molecular weight. So let's look at up. Whoop. Trying to find molecular weight. Usually it's, oh, there it is, 78. Excuse me. I could have added it up, but sometimes it's easier to look it up. So this is 78, and now let's look at 1 bromo, but of course you could just subtract it. And so this mass for bromo is 122.9 grams per mole. And so this difference in molecular mass, so this is what's going to make the difference in the boiling point. So the boiling point for this one is 47 for our chloro versus 71 degrees for our 1 bromo propane. And so naming, again, is pretty straightforward. So we want kind of the larger, we want bromine to take priority over chlorine. And so again, trying to assign your highest priorities to chlorines. And then, so the last thing is thiols. And so thiols have, again, these similar naming. So let's look at one example. And the cat's pushing my laptop off the desk. So let's see. CH3. So looking at this example, now we just start, again, where do we want to label this? So 1, 2, 3, 4, that looks good. Otherwise it's 1, 2, 3, 4. And we don't want to give sulfur that low priority. So 1, 2, 3, 4. And so now this is going to be 3-methyl. Since again, we have that methyl on that third position. And then 1-butane. And then the ending is just diol there to indicate our little diol group here. So let's look at this other one. So can you write the structure for trans 2-butene 1-thiol? So let's start with that. So trans, I know that's going to look like that. And then butane, so 1, 2, 3, 4, but it's butene since we have a double bond starting on the second carbon. And so 1, 2, 3, 4, and then we have a 1-thiol, so SH there. And so this is apparently skunk odor. So now let's look at some of these reactions. And so let's look at this little diagram there. And so these disulfide bonds, you can make them and break them by using either an oxidizing agent, so this makes them, or if you want to do the reverse, you would use a reducing agent. And I was going to pick on my ladies out there, anyone who likes hair. And I don't know why that doesn't want to move down. That's kind of annoying. Okay. Guess I won't move that. But have any of you heard of it? Owala. Let me look at how you spell it. It's this hair thing. Oh, Olaplex or something. Olaplex. And so this is for hair. And it's gotten a lot of attention recently. But what it does is it works to repair hair by acting as an oxidizing agent. And so in this case, you have your hair strands and your little thiols. And so you can oxidize them. And so this removes the hydrogen and forms these sulfur-sulfur bonds. And then you could do the opposite and break these sulfur bonds with reduction. So you would start with the disulfide and get back to the thiols. But this has been like a really good way to repair hair. So this has gotten really popular over the years. And so many people use this and they swear by it since again, it's supposed to chemically repair your hair. All right. Well, I think we hit most of the chapter, kind of covered all highlights. So Wednesday, we'll do some more review over the chapters. We can do more practices with naming, more practices with our predicting our products, and all those good things. So again, if you can't make it live, just email me questions so I can go over things. Otherwise, have a great rest of your Monday. And I'll hang around on stream. Sorry, trying to get my exit music going. So in case there are any questions, I'll be here for a little bit. Otherwise, email me.
Losing time, I'm fading fast. I just wanna make it last. Try to let go of the past. I close my eyes, embrace the blast. Sleepless nights and headache stack. Restlessness to hell and back. What's my purpose? What do I grab? I've seen a lot of change, been through a lot of pain. Some things are not the same as they were a year ago, but all will be okay. I move on each and every day. The past is where it stays, way back a year ago.